The ability to name organic molecules is an important skill that is crucial for success in organic chemistry. The general principle of nomenclature is very simple. Every organic molecule must have a unique name. Corollary to that is, given a name, you should be able to come up with a unique structure, and given a structure, you should be able to give it a name. So when we talk about names, we're generally talking about systematic names. And systematic names follow a set of rules developed by the International Union of Pure and Applied Chemistry, better known as IUPAC, back in 1892. You should be aware that there is another system of naming molecules that are called common names that do not follow the IUPAC rules. Common names will frequently be used for molecules that were discovered before 1892, but there are some classes of molecules even discovered since then that are frequently named using their common names just because that is simpler. When we get to molecules like that, I will be showing you both the common and the systematic way of naming those molecules. Okay, so how does a systematic name work? Well, a systematic name has three parts, at least in simple cases. You have a stem, which indicates the number of carbons there is in the molecule. You have an ending, which indicates the principal functional group present in that molecule. And then you will have something that comes before the stem, some combination of prefixes and numbers. And they describe the substituents. Okay, I just threw a new word at you, right? What's a substituent? Well, a substituent is simply a functional group that is bound to a hydrocarbon chain. In other words, anything other than a hydrogen that is on a chain is considered a substituent. Hydrocarbon chain may also be a novel concept. Hydrocarbons are simply molecules that contain just carbon and hydrogen. So from the tour of the functional groups, you should recognize alkanes, alkenes, alkynes, and aromatics as being examples of hydrocarbons. Okay, so we're going to start our tour of nomenclature rules by talking about unbranched alkanes. Those are the simplest molecules, and they have the ending ANE. Okay, so let's see how this works. As we've said, the stem refers to the number of carbons. So on this table here, we have the number of carbons, the stem that goes with that number of carbons, okay? So think about this as being like a foreign language. If you want to say 1 in organic chemistry E's, you will say meth. If you want to say 2, you will say F, etc. So the hydrocarbon containing just one carbon uses the stem meth and the ending ane, and that gives you the name methane, a molecule you've probably heard of because methane is the component of natural gas that's used to heat many homes. And methane has the structure CH4. 2 carbons gives you ethane, 3 carbons gives you propane. Again, another commonly used molecule that's used as a heating fuel in many parts of the country where they don't have natural gas, and also for gas grills. Butane, 4 carbons, is what's typically the fuel inside cigarette lighters. And then for the structures here on the right-hand side, you can see that they are simply straight chains. At each end of the chain, you have a carbon with 3 hydrogens, and then you have the proper number of CH2 groups in the middle of the chain. Okay, meth, eth, prop, and but are completely organic chemistry terms, and you will just have to memorize those. The stems for larger numbers of carbons actually come from the Greek prefixes. So if you know your prefixes, you might know some of these. So 5, for example, is pent. If you've heard of a pentagon, that is a geometrical object with 5 sides. That gives you an idea of how 5 corresponds with pent. Pentane being the 5-carbon hydrocarbon. Similarly, 6 carbons, you get hex or hexane. 7 carbons, you get hept or heptane. 8 carbons, you get oct or octane. Okay, you might have heard of octane as being one of the components of gasoline. You could classify gasolines as being regular, plus, or super, depending on their octane rating. None is the stem that we use for 9 carbons, and then dec for 10 carbons. After 10 carbons, we put something in front of the dec, so 11 will get undec, 12 will get dodec, then 13 is tridec, 14 is tetradec. I didn't go that far in this table, but that gives you a pretty good idea of what you do as things get larger. Okay, so unbranched alkanes are actually fairly simple. Once you know how to name one of them, you probably know how to name all of them. But if that's all there was to organic chemistry, this would be really easy. Molecules are more complex than that, and we have to modify our naming rules in order to be able to handle more complex molecules. So the next level of complexity up are what I call the simple branched alkanes. Okay, so a branched alkane occurs when a hydrocarbon chain is a substituent. Okay, and this type of substituent is generally, or generically if you prefer, referred to as an alkyl group. Okay, and so the way we name alkyl groups as substituents is by using the stem that I introduced you to for the number of carbons, but then changing the ending from ANE to YL. Okay, so a 1-carbon alkyl substituent is a methyl group. A 2-carbon alkyl substituent is an ethyl group. A 3-carbon alkyl substituent is a propyl group, etc. Okay, so a proper name for a branched alkane must show 3 things: the identity of the parent chain, the identity of the substituent, and the location of the substituent. Okay, so let's put this into practice by naming the following molecule. And I will take you through this step by step. Okay, so step 1 is to identify the longest carbon chain. Molecule like this, it is fairly easy, but if you get a more complex molecule, perhaps it will take a little effort to identify which chain is the longest. The way you do that is by counting carbons. Okay, so the longest carbon chain is the parent chain. It is the chain that runs left to right in this particular structure. It has 7 carbons, so we're going to start the name by writing heptane. This is going to be a derivative of heptane then. Okay, step 2 is to identify the substituent. Well, if the parent chain is what's going from left to right in this structure, the substituent is what's coming off to the bottom, and that is a methyl group. Okay, so if we add that to the name, this is going to be a methyl heptane. Now we have to come up with where that substituent is. Okay, so step 3 is to number the carbons in the chain so that the substituent gets the lowest possible number. Okay, so let's do that. In this case, we're going to number the chain from left to right, 1, 2, 3, 4, 5, 6, 7. And it should be fairly clear to you that the methyl group is at carbon 3. Now, sometimes I will throw a monkey wrench at you and draw the molecule in such a way that you will have to number the chain from right to left instead of left to right, or sometimes the parent chain may be running top to bottom and you may have to number it that way. So be aware of all those possibilities. We will see that in further examples. But for this first example, I kept everything simple. The methyl group is on carbon 3. So then what we do is we put a number into the name indicating the location of the substituent, and that goes at the very beginning of the name, so 3-methylheptane. Okay, at this point I want to make sure we're on the same page with a couple of rules of syntax. There is no space between methyl and heptane. Okay, methylheptane is just one word. And then there is a dash between 3 and methyl, because in general, there is always a dash between numbers and words when you're constructing a name.